Welcome to the Fraunhofer Institute for Organic Electronics, Electron Beam and Plasma Technology, the FEP, in Dresden. Today's topic is the tissue preparation of biological prostheses, especially hardware prostheses. It's a technological, innovative procedure incorporating the electron beam technology as core competency of the Fraunhofer FEP. What does it mean? What does it involve? Our so-called Sulai process is an alternative preparation procedure used to treat pericardial tissue, which is applied for biological hardware prostheses. The name Sulai stands for treatment of decellularized pericardial tissue for stabilization and sterilization by photoinitiated ultraviolet, cross-linking and low-energy electron beam. For a better understanding, let's first have a look on the heart model here. The human heart is the motor of our life, and there are so many amazing facts about it. The human heart is as big as man's fist. The human heart is beating up to 70 times per minute, means 100,000 times per day. The human heart pumps up to 8 liters per minute through our body. For this, the blood vessels in our body, the pipes of our heart, are 100,000 kilometers long. The bloodstream is regulated by the 4 heart valves, one for each of the chamber of the heart. As you can see here, the mitral valve, the tricuspid valve, the aortic valve and the pulmonic valve. During a human lifespan of about 70 years, one heart undergoes 2.6 billion opening and closing circles. The 4 normally working heart valves make sure that, firstly, the blood always flows freely in one direction, and secondly, there is no backward leakage. However, in case of a heart valve disease, the normal heart valve function is disturbed, caused by degenerative alterations like stenosis or insufficiency. A surgical operation is often the only thing that can help, especially by a high-grade stenosis. Around the world, approximately 300,000 valve operations are performed every year. About 30,000 people receive a new heart valve implant every year in Germany alone. There are 2 primary options available for the heart valve replacement based on cardiac surgery. The mechanical heart valve prosthesis can be seen on the left side, and the biological one on the right side. When selecting a prosthesis, several factors like patient's age, secondary illnesses, or life expectancy have to be taken into account. In recent years, biological prostheses, bioprostheses, have become more and more popular. What makes them so unique? What is the reason? Biological heart valves are not composed of thrombogenic materials, so there is no need for the patient to take blood-thinning medication. Bioprostheses are tissue-based valves. Over the years, there have been great advances in the heart valve technology. Biological heart valve prostheses are either made from bovine pericardial tissue or porcine heart valves. However, current biological prostheses suffer from a shorter functional life. After 10 to 15 years, 30 to 40% of all patients experience a similar level of degenerative change as they would have with a native valve. What is the reason? The tissue integrity diminishes over the time. The reasons are so believed to lie in the manufacturing process. The actual standard, also called the gold standard, is tissue fixation by use of cytotoxic substance glutaraldehyde. The remaining 3 aldehydes after fixation are one of the unresolved sources for valve calcification, leading to the loss of the function. The improvement of bioprosthetics manufacturing process opens up the possibility to increase the tissue integrity.
Now let us have a close look at the details of the pericardial tissue preparation. First of all, a fresh, sometimes still warm, bovine heart is delivered after cattle had been slaughtered. The pericardium quality depends on the cattle, breed, age and gender. The pericardium is delivered completely attached onto the bovine heart and first roughly freed from the fat residues. Then it is cut off the vessels and peeled off. Now it can be spread out flat after a cut towards the apex. In the first washing step with PBS buffer solution, the pericardium is roughly cleaned. Small fat residues are then removed and cut into square pieces. Several washing steps are carried out to rinse the tissue. This process is accelerated with the help of a shaker. The pericardial samples are now prepared for the Soulé procedure. As you can see here, the final cleaned pericardial tissue appears in a nice whitey color. In the next steps, the pericardium has to be processed in order to be usable as a part of a tissue engineering heart valve processes. The Soulé process has been established as a substitute procedure for the treatment of the pericardium. It is based on 3 different process steps: the decellularization, the stabilization and the sterilization. First step is the decellularization. Complete removal of resident cells must be guaranteed here. This avoids the rejection of the xenogenic implanted tissue later on. The pericardial tissues may be decellularized by combining the synergic action of physical agents, detergents, enzymes and chemical compounds. The treatment should not affect the mechanical integrity or the biological activity. In the subsequent steps, the decellularized pericardium has to be stabilized and sterilized. These 2 steps I will explain more detailed in the following. The preservation of decellularized pericardial tissue is carried out via photo-initiated ultraviolet pre-cross-linking using vitamin B2 riboflavin as an initiator. The final step is a treatment by non-thermal low-energy electron irradiation in order to enhance the stabilization effect and to sterilize the pericardial tissue. Here you can see the typical electron beam system, the so-called rare mode, constructed by the Fraunhofer FEP. Low-energy electrons are a versatile tool and produce numerous effects. The final goal of the lay process is to achieve a similar cross-linking degree in comparison to the conventional glutaraldehyde pericardium fixation. The evaluation of the terminal sterility has to be done as concluding microbiological test. Sterility assurance of medical devices like heart valve procedures is one of the requirements by global device regulations. A sterile medical device is one that is free from viable microorganisms. As shown here, on the left side, the pericardial tissue sample, treated by low-energy electrons, is sterile in comparison to the non-treated on the right side. Xenogenic decellularized heart valve substrates treated by the Soulé procedure has the potential to overcome the limitations of existing bioprosthetic heart valves, which have limited duration. The manufacturing process has a significant impact on the pericardium durability. Therefore, the pericardial tissue itself and the prosthetic heart valve product have to be investigated by the accelerated wear testing. As a result, the valve's life expectancy in human body can be estimated. In conclusion, the Soulé process is a promising alternative procedure for the preparation of pericardial tissue. What are the advantages? It offers the new options for longer functional life of glutaraldehyde-free heart valve bioprostheses. The Soulé-treated pericardium shows an increased biocompatibility, and there is no need for a further sterilization step. We very much hope that the Soulé process can be integrated in a customized manufacturing process in the near future. If your interest has been aroused, please contact the Fraunhofer FAP Marketing Department.